before I go on, I want to show a few compounds, acids, cannabinoid acids, which are present in the plant more than they're present in dried marijuana or dried hashish, because they change, they decarboxylate. And they turn into THC or in cannabidiol. But these compounds, people have not looked into them. These compounds are potent anti-inflammatory agents, and they have no CNS activity, to the best of my knowledge, and nobody has looked into them since we isolated and published their structures many, many years ago. I wouldn't tell you when, don't want to look that ancient, but we published them, we looked, and so that they're anti-inflammatory. As a matter of fact, we tried to look into the literature, and it turned out that a Czech group in one of the small Czech towns in Bohemia had a mixture of these compounds in their hands in the late 40s and were using them as an anti-inflammatory mixture for inflammations on horses. They were just putting the mixture on horses, and then the inflammation just disappeared. Nobody has looked into them since. In marijuana, they don't exist because they decarboxylate on smoking. But if people use the extract of the cannabis, then probably most of the anti-inflammatory portion, most of the anti-inflammatory activity is due to these particular acids. But the compound that we isolated, 1964, tetrahydrocannabinol, THC, has been looked into in great depth. Just a few weeks ago, I got an email from a young fellow in Hungary, I don't know him, and he wrote me, "Congratulations on the 40th anniversary of your paper in the Journal American Chemical Society on this compound, on THC." And I was kind of surprised and happy, really, and felt extremely ancient. After all, that's 60 years ago. But there has been a huge amount of work on THC, and indeed, for the next 20 years, people got to know a lot about the chemistry, a lot about the clinical effects, a lot about the biochemistry of THC. One thing was still unknown 20 years later. I mean, I'm speaking now of 1964 till the mid-80s. Nothing was known about the mechanism. How does THC act in the body? And the reason for that was a mistake in the literature, a mistake in research, and I'll tell you in a few seconds about it. And therefore, people didn't know whether this compound acts on something on the body, a receptor, an enzyme, anything of that sort, or it was just a very general thing. People thought that it acts like an anesthetic, like a general anesthetic acting on membranes. And even the head of pharmacology at Oxford, probably the leading pharmacologist in the world at that time, thought that it acts on membranes. Anyway, the reason for that was really a mistake, and we should always realize that mistakes do occur. For a compound to act on a specific enzyme, a specific receptor, anything that's really biologically there, it should have a very specific stereochemistry. It should be built in space in a particular way. If there are two possible kinds, one is a mirror image of the other, the two of them should not act the same way because they cannot bind. The enzymes, the receptors, all of them are built in a very specific way in space. And therefore, the other compound that will act on them has to be built so that it will be able to attach itself. The other stereoisomers will not. Well, in this case, both compounds were active, both the plus and the minus. The minus is the natural one. The plus, which we had found a way to synthesize, also was active. Well, not to the extent of the first one, but to about 20%. So people said, well, these compounds don't act on enzymes. They don't act on the receptors. Who knows how they act? Well, it turned out to be just wrong because we had synthesized a compound. We knew how to do it. We saw that it was being wrongly synthesized. People were buying starting materials from commercial companies, and the starting materials were not very pure. So we really purified the compounds, prepared the stereoisomers, and found out that the stereoisomer, the mirror image of the natural product, is not active at all. Therefore, chances were that the compound is indeed acting on a receptor, an enzyme, and something. And a few years later Alan Howlett in this country was able to show that it acts on a certain enzyme, forming cyclic, working on cyclic AMP, and later to find that there is a receptor, and this receptor was later fully identified at NIH. Now, receptors are not built in our brain or anywhere in our body, of course, or animal bodies, because there is a plant out there that will produce a compound that acts on them. That just doesn't work that way. Receptors are found in our body because we produce compound that will activate those receptors, and that's why there is an equilibrium, if you wish, between action and inaction, those receptors, and that's how one of the ways our body works. So obviously we thought that there should be endogenous compounds which act on those receptors. The fact that there is a plant compound, a tetrahydrocannabinol, a THC, which acts on those receptors is just a quirk of nature, if you wish. Anyway, it's not because of these compounds that the receptors are there. So we worked very hard for a few years, and about 12 years ago, we were able to identify, to isolate and show the structure and start biological work on a compound we call the anandamide. Ananda is a name in Sanskrit which means joy. So anandamide, and it has been thoroughly investigated in the last decade. Anandamide is one of the natural compounds which we produce and which act on these receptors and do a lot of things, a long, long list of actions. Actually, there is barely a biological system, a physiological system in our bodies in which the endogenous cannabinoids, or in short, endocannabinoids, do not participate. They are involved with a lot of other things, but they are involved in just a long, long list. Now, there is a second compound which we originally found in the periphery, the spleen. Later, other people found it in the brain. There is a third compound, and then we have another compound which seems to act on the cardiovascular system and does not act on the central nervous system. This we are going to publish shortly. So there is a large variety. The first two compounds, anandamide and 2-AG, are the most important ones. And they are found in those regions of the brain where we really should expect to see them, in the regions that have to do with movement control, with coordination, learning and memory, stress, cognitive function, etc., etc. The physiological systems and conditions affected by endocannabinoids, and this is only a partial list, and a whole list will take quite a bit more space. You can see that even this short list has quite a few actions there. Starting from appetite and feeding, we found that newly born mice, for example, that in which the cannabinoid system is blocked, do not suck. They die of hunger. They don't know they're hungry. They just don't suck, although their mother wants to give them milk. But if we de-block the blocking agent, they're very happy and go and suck. And so on, the blood pressure, blood flow, etc., down to reproduction and stress. Obviously, I cannot talk about everything here. It will take hours and days. And let's look at summary, which my good Italian friend Di Maso summarized the activity, which is really a summary. Says, well, what do the endocannabinoids do? They relax, help us eat, sleep, forget, and protect. Not remember, forget. And don't think that forgetting is less important than recalling. We should have a system to forget. Otherwise, well, if you wish, we can burst. If you go down a mall and see 1,000 faces, do you want to remember all of them? Of course not. So this is but there are also other memories, and if I have the time, I'll speak about it. There are memories that we certainly try to forget. Otherwise, each one of us will be in a constant trauma.